Kia ora. Okay, so we're going to have a look at some examples. I'm going to go through 3 examples and they cover pages 56 to 58. So the first example is this. Find the function whose gradient function is dy by dx equals 6x squared minus 6 and which passes through the point 2, 0. Now, what we have to do for these is we are going to have to anti-differentiate. That's going to find us a function which will have a plus c, and then we're going to use the point given to find the complete equation. And that's going to be the same process for all 3 of these examples, but they're just going to get a little bit more difficult with application as we progress. So what we're going to do is we're going to anti-differentiate this. So given the notation, we have a dy by dx, so that means the original function is going to be a y. So it's going to be y equals, and remember all we do is we add 1 to the power, so it's going to become x cubed, and then we divide by the new power. So 6 divided by 3 is 2. So it's going to be 2x cubed, and then over here we add 1 to the power, so that's going to make it x to the power 1, and then we divide by 1, so that's just going to keep as a 6, and it was a minus 6, so we'll keep that there. Now remember, we have this unknown space that could be a constant, so we're going to add on our constant of integration. I'm going to call it plus c. So now we have our original function, but we have to work out what c is. Luckily we have this point here, so we've got pretty much what we're dealing with here is some sort of positive cubic, right? And we know that our positive cubic goes through the point 2 and 0. I don't know where it is on the curve. Actually, I do, because I've got a picture of it flipping right over here. Dang it, I gave you guys the answer from the beginning. So what we know is that function passes through a point 2, 0. So you won't be able to see this usually, but I just want to show you why. So we know that our function passes through 2 and 0. So what we can do is we can substitute these in. So we have our x value and our y value. So that's an x, y, 1, y, 1. So we know that our function goes through there. So we can substitute in here. See how we've got this unknown y, an unknown x, and an unknown c. So if we get rid of 2 of those unknowns, so we put in our 0 here. So let's do some substitution. Equals 2, and then we will substitute in our x here to the power 3 minus, and then we'll substitute in our x again, 2. And now we have an equation with 1 unknown. So that means we can solve for this. So let's do that. 0 equals 2. 2 to the power 3 is 8. 2 times 8 minus 6 times 2 is 12 plus c. So we've got 16 minus 12. Well, maybe I should do this a little slower. I'm going to do it a little slower. 16 minus 12 plus c. 0 equals 4 plus c. So then c equals negative 4. That's showing like absolute full working. The other thing is, before you're finished, you need to actually rewrite it out again. So now that we have found our c value, we know that c equals negative 4. We just need to substitute that back into our original function. So it's going to be y equals 2x cubed minus 6x minus 4. Alright, so that is the function whose gradient function is this, and it passes through the point 2, 0. Let's have a look at it over here. So I've got that. F of x equals 2x cubed minus 6x minus 4. So we were able to use the derivative function. We anti-differentiated that, and we found this. Let's add a little slider in. We found that the actual original function could be anywhere here, but then that got locked in place because we knew that it passed through the point 2, 0. So let's just draw that point 2, 0. So we knew it had to be the only one of these functions that passes through that point. I just want to make that super clear for you guys. So see how there's only actually one time where that solution works. So we keep moving it until it perfectly fits in there. And it turns out it's when c is equal to -4. So that's how we were able to then substitute that in, make it -4, and then that is the function that passes through the point 2 and 0. So that's the first example, and that's pretty much all of pages 56 and 57 are practicing this sequence of steps, and then this sequence of steps is going to be used in some applications, but it's going to be the same sequence of steps, just a little bit more problem solving that you've got to deal with. Okay, let's have a look at the next question. So the next question is this. If dash of x equals -12 x squared plus 3, and the original function's local maximum has a y value of 3. Now this is all on page 58. So what we know is that this is the derivative, and the original function's local maximum has a y value of 3. This here is essentially giving us a coordinate. It's essentially a coordinate. The problem is it's going to require some problem solving. So let's have a look at how we could do that. So let's just find the antiderivative first. So f of x is going to be, so let's do the process. So we add 1 to the power, x cubed, and we divide by the new power. -12 divided by 3 is going to get us -4. Plus 3. So then all that happens when you anti-differentiate is that becomes plus 3x. And then we have our constant of integration that we add on. So then we're going to have to solve for c. Now, what we know is that the original function's local maximum has a y value of 3. I'm just going to actually hide this away for a second, because I don't want to confuse you guys. Now, let's do a little bit of thinking. Now, what is the original function? Let's have a look. We can see that it is a negative cubic. The original function, see, we found the original function is a negative cubic. So what does a negative cubic look like? It's a cubic shape, but it's going down more. Oh shucks. That's kind of pretty. Right, so we're looking at a negative cubic. We can get that information after we anti-differentiate, because we have a negative symbol and it's to the power of 3. That's the highest power here. It doesn't matter about these two bits of information. We're only looking at the highest power. And we know it's a negative cubic. Now we know that the local maximum, so where is the local maximum? It's right here. So we know that our local max has a y value of 3. So we don't know what its x value is, but we do know what its y value is. So right now what we know is it's something, comma, 3. This is all we know about our coordinate so far. So we're going to have to find a way to get our x coordinate, because we need our output value, our y, and we also need a value for x so that we have only one unknown in our equation so that we can solve for that unknown. So how are we going to find this? Well, it turns out that if we do calculus, we can find the coordinates of turning points quite easy. How do we find turning points? Find the coords of the TPs. So we're going to have to go back to some derivative stuff, right? How do we find the coordinates of the turning points? We find the coordinates of the turning points when the function's derivative f dash of x is equal to 0. It's when the derivative is equal to 0, because as you can see here, at this point the gradient is 0. And also here, the gradient is 0. So let's use our derivative. Well, luckily they've already given us the derivative, right? So we're going to go 0 equals, in our derivative, negative 12x squared plus 3. Okay, this looks like it's going to be quite easy to solve. So what I'm going to do to solve this is I'm going to bring that onto the other side. 12x squared equals 3. I'm then going to divide both sides by 12. X squared equals 3 over 12. And then let's just do that. X squared equals 3 over 12. What is that? 1 over 4? Okay, so now what we do is we take the square root of both sides. X equals plus or minus square root of 1 over 4. Luckily, I know how to do this. We just do the square root of the top and the square root of the bottom. So x is equal to plus or minus. So what's the square root of 1? It's 1. And what's the square root of 4? It's 2. So x is equal to plus and minus half. So we're going to have to go to our picture now. And which one comes first? The first one is going to be the smaller of these two numbers. Maybe I should write them out. So x1 is going to be the smaller of these two. So it's going to be negative 0.5. And x2 is going to be positive 0.5. So therefore our local maximum is going to happen at x2, because it's the greater of these two values. It goes from left to right. So that one's going to happen at x equals negative 0.5. This one happens at x equals 0.5. So we now know this value. It's when x is 0.5 that our local maximum occurs. So now we have that coordinate, right? So this is just a complicated way of telling you guys a coordinate, but it requires some calculus to actually find that value and some knowledge of what the shape looks like as well. So this question's pretty good. It's got quite a bit of problem solving. I like it. Okay, we aren't done yet though, are we? What we've got to do now is we have our function. We're going to bring that over to here. And we're going to use this coordinate as well. So it's going to be, our y value is 3. I'm going to make it clear that I'm joining these two things together. Our y value is 3 equals, and negative 4. Our x value is 0.5 to the power 3 plus 3 times 0.5 plus c. So see now how we have one unknown, and we just got to solve for it. So let's do that. 3 equals 0.5 to the power of 3. That half to the power of 3 is 1 over 8. Negative 4 times 1 over 8 is negative, I want to go to fractions so badly, but I shouldn't. 0.5 plus 1.5 plus c. Okay, so let's bring all of the numbers over to this side. So it's going to be 3 plus, let's join these together first. Negative 0.5 plus 1.5 gets us to 1, and then 3 minus that 1 is going to get us to 2. 2 equals c. So therefore our function is going to be this. Equals negative 4x cubed plus 3x plus 2. That is our original function. Let's have a look at that. Okay. Ooh, let's make sure I got it right first, obviously. Yes, sweet. Okay, so pretty much what we got again was we found our original function by anti-differentiating. We then had this floating c, and what we found out was that it was where the local maximum was. So the local maximum had a y value of 3, and we found out using our derivative that the local maximum is going to occur here. By substituting 0 into the derivative, we found negative 0.5 and positive 0.5. We worked out that this one had to be our local maximum because it was a negative cubic, and the local maximum happens after the local minimum. So we then knew that it was at the x value of 0.5. And then from there, we also knew the y value. So when we put that in, they already gave us the y value. So we then had a coordinate where we knew that the local maximum was happening. And then all we did was solved for c by substituting that coordinate in, and that found us that c was equal to 2. So that's how we do page 58. Okay, let us have a look at what happens on page 59. So on page 59, they're going to start giving you some pictures, and these have been quite common in the calculus externals for level 2. What they do is they give you a couple of pictures. They'll give you one of the original function and one of the derivative. Some people will just use algebra, and because there's pretty much, they'll make it so that there's like one point that's really clear where that intersection is. But sometimes if you find some other point, you might be able to just use algebra to find the equation of this negative parabola. But what you actually have to do is use calculus. So pretty much we've got this one coordinate here for the original function, and we have to use the derivative, which is a straight line graph, to find that parabola. So pretty much we're going to have to use some information we know about finding the equation of a straight line. So what's the equation of a straight line? It's y equals mx plus c, right? Where m is the gradient and c is the y-intercept. Right, so we've got all of that information here. Oh, if I'd labeled it, which I haven't really. Let's just do some labels. Let's say this is 4, this is 4, this is negative 4, and this is negative 4. Okay, so that means that we've got our y-intercept here, and our y-intercept is c, which equals, it's happening at negative 2. So we've got our y-intercept. Now what about our gradient? Our gradient, we need to pick 2 points. So I'm going to pick this point and this point. And a gradient is found by getting our run and our rise. So here we can see that from this point to this point, our run is 2. So our run is 2. And our rise, so from here to here, it actually went down 2. So that means our gradient, so we found our c value was negative 2, and now our gradient is going to be our rise over our run. So it's negative 2 over 2. Negative 2 over 2 is negative 1. So using this picture, we can find the equation of a straight line. So that means that f dash of x is equal to, so what is it? Mx plus c. It's going to be negative 1, which is m, x plus c, which is negative 2. Oh man, I did that so ugly. Let's clean that up a little bit. F dash of x equals negative x minus 2. So this is the equation of the derivative. So then from there we can find our original function with a c value. So it's going to be f of x, and let's anti-differentiate this. F of x, so what do we do first? We add 1 to the power, so it's going to become x squared, and then we divide by the new power, so it's going to be negative x squared over 2. And then here it's going to go to negative 2x, and then we have to remember our constant of integration. Let me just refocus that. Okay, so we've got a function now, and they usually won't do this, but there will be 1 or 2 points on that function that are really clear. They will be points that are like happening on intersections. Let me zoom in and focus. So pretty much, when they give you a question, focus on me, please. No, come on. Come on. Kidding me? Stein the flaming Christ. Yes. So I've labelled this one because I've tried to make this a really clear one. It might also be that this point's really obvious. It could also be something that's happening over here is obvious, something here is obvious. But they'll give you one point that's really clear, and I've just labelled it because my penmanship was a little bit off today. So we've got the point 0,3, but you'll normally have to find that yourself. Okay, anyway. So now that we have that point, we know the drill. And the drill is, we've got a coordinate, and that is 0,3. So we want to find that at 0,3. So let's substitute those points in. So x is 0, f of x is going to be 3. So 3 equals negative 0 squared over 2 minus 2 times 0 plus c. Well, would you look at that? This is just going to get to 0, this is just going to get to 0, so voila, 3 equals c. So that means our function f of x is just negative x squared over 2 minus 2x plus 3. Let's have a look at that. So I've got that up here. As you can see, here's the function. I made sure that it goes through this point, 0, 3. So here is our original function. F of x equals negative half x squared. This is just another way of writing negative x squared over 2. This is probably a slightly less fancy way to do it, to be honest. Yeah, so we got our derivative. Our derivative had like a little floater again. That little plus c made it float. But we had to lock it in because we had this coordinate here, 0, 3. So yeah, that is page 59. I hope that is helpful.